most important element in the study of celestial navigation is time. The reason for this is that the apparent motion of all bodies on the celestial sphere can be measured in units of time. For example, observe the sun as it apparently moves on its diurnal circle. It travels at an angular speed of about 15 degrees, or 900 minutes of arc per hour. If we take an observation of the sun and note the time of the observation, in effect, we stop its motion, like this. Now we can see that the sun marks one angle of a spherical triangle at M, the pole another at P, and the apex of the third angle lies on the celestial meridian at Z, which you will remember is the zenith of the observer's position on the Earth. Here then we have PZM, the astronomical triangle of navigation. This angle, T, is the meridian angle, which but a moment ago was increasing to the westward as the body moved on its diurnal circle. Obviously, therefore, it has some connection with time. As this side of the triangle is the colatitude, and this side is the polar distance, it is necessary that we determine this angle, T. Knowing the two sides and the angle T, we can solve the triangle for this side, the co-altitude, and this angle, the azimuth angle. These are the elements of the triangle which we must know if we are to determine, by observation of celestial bodies, just where we are on the surface of the sea. Now, astronomers have very accurately charted the positions of the heavenly bodies and can tell at any instant of time just exactly where any star, planet, or the sun or moon is located. This information is tabulated in an almanac, and the argument against which it is tabulated is time. Therefore, it is vital that the navigator know what time is and how it is derived. To see what time is, let us consider the real motion of the Earth in the celestial sphere. Locate a position on the Earth and indicate a terrestrial meridian. If a reference point be established on the celestial sphere, we can see that the period between two successive crossings or transits of the meridian can be used as a unit to measure time. Therefore, time is a measure of the period of rotation of the Earth on its axis. This period of rotation is called a day. The rotation of the Earth on its axis is perfectly uniform and regular. That is why this rotation is used as a basis for measuring time. In navigation, we use three kinds of time, each of which is determined by use of a different reference point for measuring the period of rotation. The first of these is apparent time, which uses the apparent or true sun as a reference point. The second is called sidereal time, which uses this intersection of the ecliptic and the equinoctial, called the March equinox, as its reference point. The third is called mean time or civil time and uses a mean or imaginary sun as its reference point. Suppose we travel to the point on the celestial sphere where the March equinox is located. Observe that as we move away from the Earth's orbit, the distance between the positions at the ends of the orbit becomes less and less until, at the infinite distance of the March equinox, the distance can be considered zero. Now enlarge the Earth until a meridian is visible. We see the Earth rotating on its axis, but from the great distance of the March equinox, it appears to be stationary in regard to the motion in its orbit. Each time this meridian crosses the line between the Earth and the March equinox, one rotation has taken place, and 1 day has elapsed. This day is called a sidereal day. Now we will travel through space toward the Earth until we approach near enough to see the Earth's complete orbit. In order to have a regular succession of the seasons, the period of time required for one complete revolution of the Earth in its orbit has been called a year. As the Earth rotates 366 1/4 times while making one complete revolution, this meridian transits the March equinox 366 1/4 times, and there are 366 1/4 sidereal days in a year. The distance between the Earth and Sun, as compared to the distance between the Earth and the March equinox, is quite small. The Earth's motion in its orbit is negligible with respect to the March equinox. If there were a star at the March equinox, the parallel light rays from that star to the Earth could be represented by this gray area. From this position, we can see the lower branch of a meridian directly toward the Sun and the upper branch toward the March equinox. Now, as the Earth rotates and at the same time moves along its orbit, note that as the upper branch of the meridian makes one revolution and transits the March equinox, the lower branch must move a little further to complete a transit of the Sun. It is evident that it is taking a little more time to complete a day with reference to the Sun than it is with reference to the March equinox. As this motion of the Earth continues, we find that at the end of one revolution in its orbit, the Earth has lost exactly one solar day. There are, therefore, only 365 1/4 solar days in a year. The relation between the solar days and the sidereal days in a year can be established by remembering that as a solar year extends over the same period of time as the sidereal year, but has one less day, the days in a solar year must be a little longer. In fact, a solar day is 3 minutes and 56 seconds longer than a sidereal day. Consequently, solar hours, minutes, and seconds are proportionately longer than sidereal hours, minutes, and seconds. It is interesting to note that the solar day was based on transits of the lower branch of the meridian, while the sidereal day was based on transits of the upper branch of the meridian. The lower branch is used as an origin for measurement of civil time, because it is more convenient to commence a new day at midnight. Our normal business life, as well as navigation, would be rather difficult if the day and consequently the date changed at noon, the time of upper transit of the Sun. As time based on the Sun's apparent motion, called apparent time, is a time in which we are particularly interested in the study of practical navigation, let us consider it in some detail. We have been considering the real motion of the Earth with respect to the Sun and the stars. However, since we must view the heavens from the Earth, it is convenient to assume that we are at the center of a great sphere of infinite radius, and that the heavenly bodies move about us on this celestial sphere. This motion is called the apparent motion of the solar system, and is composed of the Earth's rotation, the real motion of the bodies in space, and the motion of the Earth in its orbit. Because of the inclination of the equinoctial to the ecliptic, and because the linear speed of the Earth in its orbit is variable, the apparent motion of the Sun is not uniform. For this reason, it would be difficult to construct a clock capable of keeping this irregular time. Therefore, a mean or imaginary sun is used. This mean sun is assumed to have a uniform rate of motion with respect to the Earth, and that rate of motion is equal to the average rate of the apparent or true sun during a year. The time measured by the mean or imaginary sun is called mean or civil time. The time measured by the apparent or real sun is called apparent time. As the mean sun is imaginary and the true sun does not have a uniform motion, how then is correct time to be determined in actual practice? It is evident that some base other than the sun must be used. This base is the March equinox, whose location with respect to the stars is accurately known. As the apparent motion of the stars is nearly uniform, and the variation in their positions in the celestial sphere is exactly known, the time of transit of any star may be observed and the position of the March equinox accurately established for that instant. Time measured relative to the March equinox is sidereal time, which we have previously discussed. Sidereal time is converted into civil or mean time, and the mean time is transmitted for correction of timepieces all over the world. To see how time is determined, we will make a short visit to the United States Naval Observatory in Washington. To observe the stars, this instrument, called a photographic zenith tube, is used. With the zenith tube, visual observations of the transit of a star are no longer necessary, and since all observations are recorded photographically, results are much more accurate. From the images on the photographic plate and the automatically recorded time of the exposures, it is possible to determine the time of transit. By comparing the standard clock time with the computed time of transit, the clock error is determined. These standard clocks are specially designed and are kept in a vault constructed to keep the temperature and the air pressure constant. The clocks are never disturbed except when it is necessary to repair them. Now, the computed time and the time kept by the clock is sidereal time. This is converted to mean or civil time, which is sent out by telegraph and by radio to all points of the country and to ships at sea. The ships correct their chronometers, and in this way they always know the correct civil time. By definition, a solar day or sun day is the period between two successive transits or crossings of the lower branch of a meridian by the mean sun. The day commences at the first transit and ends at the second transit, when a new day begins. For navigational purposes, the day is divided into 24 hours, but this 24 hours is not further subdivided into periods of 12 hours, as is the general practice in civil life. Because of this, we do not have AM and PM in navigation, but speak of 1600, which is the same as 4 p.m., or 1945, which is 7:45 p.m. When the mean sun transits the lower branch of a meridian, it is the beginning of a day, or 0 hours. And when the mean sun transits the upper